In the previous classes, we have discussed about moment of inertia and rotational motion of a rigid body. I will work out numerical problems in one class. Today, let me start the remaining one more chapter, waves, which is just a 3 hours topic. So the content I will cover in today's class and problems on waves and problems on moment of inertia will be worked out in one more class. And this recorded session will be shared to your group, second sem BSc students group, in YouTube form. You can go through the recorded class and the content of the lesson will be shared in the same group. Go through the content and prepare for all the exercise questions and also try to answer a few years question papers, at least 3 years question papers. Go through the type of questions given, because main question carries 8 marks and numericals carries 4 marks. They are very important. Descriptive answer you should be able to write correctly for 8 marks. Now let us start the topic waves. I think you have studied about what is wave and about wave motion with a lot of examples in PU at PU level. Wave is nothing but a sort of disturbance created in a medium. You can think of any number of waves. For example, sound is a wave, light, water waves, waves along a rope, waves in a stretched string. So in all these things, which moves in the form of wave is nothing but disturbance. The disturbance created in the medium will make the particle of the medium at the point of disturbance to vibrate simple harmonically, and then the energy will be transferred to the next particle. When the next particle starts vibrating, the previous one will come to rest. Likewise, energy will be transferred from one vibrating particle to the next, and thus the energy is transmitted in the form of wave. Waves are motions that carry energy but not matter. Material particles do not move along with the wave. Remember that. So they carry only energy from one place to another. A wave is a form of disturbance which travels through the medium due to repeated periodic motion of the particles of the medium about their mean positions. The disturbance is handed over from one particle to the next. We call it as wave motion. The mode of energy transfer in which a disturbance advances in the forward direction by affecting the medium without mass transfer is known as wave motion. You can define wave motion in different way. Wave motion means it is only the propagation of energy through the medium in the form of repeated vibrations of the particles of the medium. That's called wave motion. Transference of various forms of energy like sound, heat, light, X-rays, gamma rays, radio waves, shock waves, etc. takes place in the form of wave motion. So you can think of plenty of examples for wave motion. Almost all the things that we receive around us, even including sunlight, solar energy or stellar energy, it's all due to wave motion. For the transference of energy through a medium, the medium must possess certain physical properties such as elasticity, inertia, density, etc. This is with respect to the mechanical waves. Mechanical waves, for the propagation of wave through the medium, it mainly depends on elasticity of the medium, density of the medium, and the inertia of the vibrating particles. However, electromagnetic waves can travel through vacuum. It does not depend on these properties of the medium. Now let us see what are the characteristics of wave motion in general. First point, a wave is a form of disturbance which propagates in the medium. So therefore the conclusion is wave is just an energy which is passing through the medium. Second point, when a wave propagates through a medium, the disturbance travels outwards. The particles of the medium do not travel and vibrate about their mean positions. It means the disturbance travels in all the directions, whether it is a two-dimensional wave or a three-dimensional wave. It will make the surrounding particles to vibrate simple harmonically, and they in turn transfers the energy to the next set of particles, and thus all the particles along the wave motion vibrate simple harmonically about their mean positions. Third point, there is a definite phase difference between every consecutive particle. So the particles are vibrating, there's definitely a phase difference between the vibrating particles because the previous particle and the next particle do not have same number of vibrations. The number of vibrations they complete depends on the propagation of energy through that point. So therefore, phase is different at different points. The velocity of wave is different from the velocity of the particles. The particles vibrates with certain velocity, that is called particle velocity, whereas the energy transference from one vibrating particle to the another particle, that is wave velocity, both are different. The velocity of the wave is constant in a medium, but the particle velocity is different at different points. For example, in stationary waves, the velocity of the wave is zero, but the particle velocity will be different at different points. Even same thing you can observe during wave motion. Sixth point, wave motion is possible only in media which have the property of inertia and elasticity. This is the main thing. The medium should have inertia to restore the vibrating particles to their resting position, and also elasticity. These two are important properties for wave motion in a medium. Seventh point, the energy of the vibrating particle at the extreme position is wholly potential, and in the mean position it is completely kinetic. So this is with respect to vibrating particle. When they crosses the mean position, remember the particle will have maximum speed, maximum velocity, maximum kinetic energy. Whereas the particle reaches the extreme points during their vibration, the potential energy will be maximum, kinetic energy will be zero, even the velocity of the particle will be momentarily zero at that point. And the last point, during wave motion, only transfer of energy takes place from one point to another. So these are some characteristics of wave motion which can be applied to sound, light, or any other form of wave. So in the examination, if any 2 marks or 4 marks question is asked, you can write maximum of 4 characteristics of the wave. So I have explained 8 characteristics of wave motion. Please go through that. The next one is, let us understand what are the two major types of waves. So depending on the vibrations of the particles of the medium, how they vibrate with respect to passage of the wave, we have two types of waves, transverse and longitudinal waves. Transverse wave means the particles vibrates at right angles to the direction of propagation of the wave. Example, waves traveling along a stretched string waves on water surface, electromagnetic waves such as light, ultraviolet, infrared, etc. Even waves along a rope, they are all transverse waves. And remember, transverse wave motion is not possible in gases and only in solids and liquids you can think of transverse wave motion. And remember, transverse waves consists of crusts and troughs. The elevated portion we call it as crust, and the depressed portion we call it as trough. So alternately, you will have crust, trough moving in transverse wave motion. A crust and an adjoining trough constitutes one wave. We call it as one wave or one wave pulse, and a succession of them we call it as wave train or continuous wave. So this is about transverse wave. Let us look at the diagram after discussing longitudinal waves. Longitudinal waves means particles of the medium vibrates parallel to the direction of wave motion. Now look at these diagrams, you will understand. The first diagram, a tuning fork is set into vibrations. It will push the layers of air on either sides all around the vibrating prongs. So the air particles, layers of air gets compressed. We call this as compression, where the lines are very close to each other. And these are called rarefaction. When the prong of the tuning fork moves to the opposite direction, a rarefaction will be formed. So thus, when the prongs continuously vibrates, it will set compressions, rarefactions, which moves through the medium. This is how sound waves in air travels. You cannot see, you can only picturize, you can imagine like this. When sound travels in air, it will be in the form of vibrations. The layers of air gets compressed, that is called compression. And when the prongs moves to the other side or vibrating particle moves to the other opposite side, a rarefaction will be found where the density of the medium is minimum. At compression, density of the medium will be maximum. Even the pressure will be different. It is maximum at compression and minimum at rarefaction. Thus, compressions and rarefactions are formed alternately. Here you can see the particles are vibrating along x-axis in this figure. Even the wave is propagating along x-axis. It means particles vibrations are parallel to the direction of wave motion. So thus, sound in air is a longitudinal wave. Similarly, you can think of a spiral spring, helical spring. In a helical spring, you can see the compressions and rarefactions will move along the length of the helical spring. The next diagram shows you transverse wave. This elevated portion is called crest. I think all of you know all these things. These are all review of what you have studied at PU level. The depressed part is called trough, crest, trough, crest, trough are formed continuously, one after the other. They travel in the form of a train. We call it as wave train. So here the energy is propagating along x-axis. That is the direction of propagation of energy. While the particles are vibrating perpendicular to x-axis, it is along y-axis or negative y-axis. Thus, particles' vibrations are at right angles to the direction of propagation of the wave. That is the nature of transverse wave. So if you vibrate a long rope, you can see how crust and troughs will travel along the length of the rope. That's the only thing you can see. Other transverse waves like electromagnetic waves, we cannot see, but they consist of crust and trough. Their nature is also transverse wave. This is about the types of waves. Next, some terms connected with wave motion, vibration or cycle. If a particle completes one to and fro motion about the mean position, we call it as one vibration or one cycle. Amplitude refers to the maximum displacement of the particle from its mean position to its extreme position. That we call it as amplitude. In the figure you can see amplitude. Small a denotes amplitude, which is the displacement from the mean position to one extreme position. Amplitude is A. Next, time period. It is the time taken by the particle to complete one vibration. So remember, when the particle completes one vibration, one crest and one trough will be formed if it is transverse wave, or if it is longitudinal wave, one compression and one rarefaction will be formed. Therefore, time period refers to time to set up one wave pulse. But the easier way to define time period is, it is the time taken by the particle to complete one vibration. Frequency, denoted by small f, refers to number of vibrations per second, number of cycles per second. So frequency is 1 over period, or period is 1 over frequency. These are important relations. Wavelength refers to the distance traveled by the wave in one time period, not 1 second, in one time period. In a time equal to one time period, the distance traveled by the wave, we call it as wavelength. It is also defined as the distance between two consecutive particles of the medium having the same state of vibration. So remember, wavelength is the distance between two consecutive points which are vibrating in same phase. Or it can also be defined as distance between two consecutive crests or two consecutive troughs in the case of transverse waves. And in the case of longitudinal wave, we can define wavelength as the distance between two consecutive compressions or two consecutive rarefactions. It is measured in meter. Next, to understand what is phase. Phase is defined as the ratio of the displacement of the vibrating particle at any instant to the amplitude of the vibrating particle. Let me put mathematically, y by a. Y is the displacement of the vibrating particle at any instant of time, and a denotes amplitude. So y by a ratio, it has no units. It is measured in angles, that is radians. We call it as phase. It denotes the state of vibration of the particle. And then wave number, denoted as k. It is defined as the number of waves in unit distance. We call it as wave number. It is given by 1 over lambda. Therefore, it can also be defined as reciprocal of wavelength. Wave number can be defined as reciprocal of wavelength. And k, which is 2 pi by lambda, is called wave constant or propagation constant. No particular definition for this term. 2 pi by lambda is called propagation constant. How the wave propagates through the medium mainly depends on this constant k. And then wave velocity. Wave velocity is the distance covered by the wave in 1 second and is called wave velocity. Distance traveled by the wave in 1 second is called wave velocity. So remember, wave velocity is different from particle velocity. Next, you know the relation between frequency, wavelength and lambda. Frequency, wavelength and velocity of the wave. So wave velocity, as you know, distance traveled by time taken. If distance traveled is lambda, time taken will be 1 period. Look at this equation. Wave velocity v is wavelength divided by wave period. That is lambda by capital T. But 1 over T is f. Therefore, v equals f lambda. So there is a relation between wave velocity, frequency and wavelength, which may be asked for 1 mark or 2 marks question. Next, let us derive expression for wave motion. That is expression for a one-dimensional progressive wave. A plane progressive wave is one which travels onwards through a medium in a given direction without attenuation. So progressive wave means wave which travels through the medium with a definite velocity. That is, with its amplitude constant, amplitude should not change. A progressive wave may be transverse or longitudinal. In either case, however, there exists a regular phase difference between two consecutive particles of the medium. Suppose a wave originates at point O. Look at the figure. Suppose a wave originates at point O, travels to the right along the x-axis, that is as shown in the figure. The displacement of the particle moving simple harmonically in a medium is given by, so y is equal to a sin omega t. It represents simple harmonic vibration. Look at this figure. There is a wave traveling along x-axis. O is the origin from where the disturbance is generated. P is some arbitrary point at a distance x. And now consider another particle P at a distance x from the first particle O to its right. The displacement at P is given by, so displacement at O is a sin omega t, and disturbance at point P can be written as y is equal to a sin omega t minus phi, where phi is a phase difference between the particles O and particle at P. For a phase difference of 2 pi, the part difference will be lambda. You know the relation between phase difference and part difference. So the phase difference is 2 pi. Those 2 points will differ by 1 wave pulse. Therefore, the path difference is equal to 1 lambda. Suppose for a phase difference of phi, the phase difference x is given by x is equal to lambda by 2 pi into phi. Therefore, phi is 2 pi into x by lambda. Now let us substitute this in equation 2. In place of phi, you write 2 pi x by lambda. You will get y is equal to a sin omega t minus your phi is 2 pi x by lambda. Now write omega as 2 pi by capital T, or you write 2 pi by lambda as k. That is better. 2 pi by lambda is k. Therefore, you will get the equation y is equal to a sin omega t minus kx. This is a standard form of writing wave equation for a one-dimensional wave traveling along the positive x direction, where capital A denotes amplitude of the wave. Omega is angular frequency, which is 2 pi f or 2 pi by capital T. Capital T is period and small t is the instant of time, minus k. K is propagation constant and x is the distance traveled from the origin to the given point. So in this equation 4, which is a standard form of writing one-dimensional wave traveling along the positive x-axis, and here k is 2 pi by lambda, which is called propagation constant, lambda is wavelength of light, and omega, remember, it is called angular frequency, angular velocity, or angular speed. Measured in radian per second, it is equal to 2 pi by capital T. Capital T is period, but 1 over capital T is f. Therefore, omega is 2 pi f. If we substitute for f is v by lambda. We can also write omega as 2 pi v by lambda. Substituting the values of k and omega in equation 4, we can write different forms of progressive wave. Look at these equations. Y is equal to a sin 2 pi by lambda into v minus 2 pi by lambda into x. You will get y is equal to a sin 2 pi by lambda into vt minus x. This is a second form of writing progressive wave. Suppose instead of minus Vt minus x, if you put Vt plus x, similarly A sin omega t plus kx, it represents wave traveling in the opposite direction. That means a one-dimensional progressive wave traveling in the opposite direction means negative x direction. Particle velocity. Differentiating equation 5 with respect to time t, we get v particle velocity is dy by dt, which is equal to 2 pi a into nu by lambda into cos 2 pi by lambda into vt minus x with negative signs or no negative sign here. This is particle velocity. So relation between particle velocity and wave velocity. Differentiating equation 5 with respect to x, we get dy by dx equals 2 pi by lambda into a into cos 2 pi by lambda into vt minus x. This is equation 7 we are writing. Here 2 pi by lambda, v is missing. You should include v here. Dy by dx is differentiating equation 5 with respect to x. Sorry, it is not with respect to t, with respect to x. If you differentiate with respect to x, you will get equation 8. So from 7 and 8, look at equation 7 and equation 8. So v particle equals dy by dt, which is equal to minus v into dy by dx. So this is a relation between particle velocity v and wave velocity v. Particle velocity means dy by dt, particle velocity. Small v is wave velocity. Just remember the relation. The derivation steps are not required. To work out the problems, you remember this relation. And one more, differential form of writing wave equation. You just differentiate equation 7 again with respect to time t. That means equation 7 is this. Dy by dt is equal to 2 pi av by lambda into cos 2 pi by lambda into vt minus x. So if you differentiate with respect to time again, you will get d square y by dt square, which is equal to minus 4 pi square v square by lambda square a sin 2 pi by lambda into vt minus x. So you will get d square y by dt square equals minus, this becomes omega square into y. So d square y by dx square equals, same continued, a sin 2 pi by lambda into vt minus x, you can write it as y. You will get d square y by dx square. It is equal to v square into d square y by dx square. This is called differential equation of wave motion. So now let me stop at this stage. Two important derivations are there, which I will take it in the next second lecture on waves. This is first lecture on waves. In the next second lecture on waves, I will work out the derivation expression for velocity of transverse waves in a uniform string.